Actually, I don't think we've done any yet, so periodic trends it is. Okay. Yeah, shut up. Let's see if I can't turn this off. There we go. Okay. So, last time we were talking about effective nuclear charge. And we saw that we could kind of estimate it by using the atomic number and the core electrons. And so this tells us that the effective nuclear charge is roughly the same thing as the number of valence electrons. Right? Since to find the valence electrons, we could do the same thing, right? We could take atomic number minus the core electrons. That would give us the valence electrons. So we're basically able to show here that our effective nuclear charge is roughly equivalent to the number of valence electrons. And we're going to be using this to kind of predict some properties based on the elements and their position on the periodic table. So with that being said, there's another trend that we want to look at. So using this, we would expect the effective nuclear charge for lithium to be 1, for sodium to be 1, and for potassium to be 1. But in reality, the effective nuclear charge actually is bigger towards potassium's end. And let's take a moment to kind of think about why the heck that is. If we go ahead and look at the electron configurations of these atoms, what we see here is, we have more, electrons as we go into potassium, but we maybe remember that, if we go back to our kind of like fake atom, where we had, orbits in this Bohr model. We know that the third one is a lot bigger than the second one, right? And this is also true for the quantum mechanical model. So like the one that we use now with all the SPDF stuff, we know that the third one is bigger. And so what we're going to actually see is that the bigger outer shells have more diffuse core electrons. So what that means is that while yes, the n equals 2 and n equals 3 for potassium have the same number of core electrons, the core electrons that are in the third one are going to be more kind of spread out. They're diffuse, they're spread out. And so the one that we're looking at, the valence shell, which is the fourth one for potassium, it has less kind of chance to be blocked by the core electrons just because they're more spread out. And so they have less shielding of the nucleus. All right, so because the electrons in the third shell are spread out more, because it's a bigger shell, the n equals 4 valence electron can kind of, get a little bit closer. So it's kind of can feel the positive nucleus a little bit more as a result. So we're not going to actually have to worry about using this in calculations, but what we want to understand is that the more shells we have, that means, oh my god, Shane, let's see. What is the inverse square law? Is that like something to do with, well, let's find out. To the Google I go. Oh, okay, yeah. Then you're okay. Yes. Sorry, I guess I did not remember the name from physics of that sort of thing. So it's just a physical law. Like, the further you are going in kind of similar ways, the more diffuse you're going to be. It's the same thing. So, but for physics. Okay. Point of this, though, was bigger N means bigger effective nuclear charge. We are not going to calculate this, so we're going to be using our Z as if it were 1 for these ones. But it's important to understand that the bigger your atom is, the more shells you have that are occupied, the bigger your effective nuclear charge is going to be. So that tells us as we go down the periodic table from lithium to sodium to potassium to rubidium, whatever, we're going to get a bigger effective nuclear charge. All right? That's just one more thing that we're going to want to worry about. Okay? So that's one thing. We also can tell that positive, because the nucleus is positive. However, it doesn't really matter for us because we're not going to necessarily calculate anything with it. We're just going to be using the concept of effective nuclear charge to illustrate these points. So as long as we understand these two, we'll be okay. Mostly, though, focus on this one. This one is going to be the big thing. So as long as we understand it increases going left to right, that's okay. And remember, going left to right, we're increasing the number of valence electrons. Right? So if you think sodium has 1, magnesium has 2, aluminum has 3, what's after aluminum? Silicon has 4, phosphorus 5, sulfur 6, chlorine 7, right? So we're going to the right, and so we're going to be increasing our effective nuclear charge. So, with that in mind, let's go ahead and start actually talking about properties. So while atoms are not technically spherical, we still kind of describe it as if they were spherical, but that's okay. We can pretend. So the first trend we're going to look at is atomic size. And so let's analyze this kind of under the lens of effective nuclear charge. So remember that Z effective nuclear charge is basically a measure of how much the valence electrons feel the nucleus. So remember how much the valence electrons feel the nucleus. And so that means that the bigger that is, the electrons are going to be attracted to the nucleus more. Right? Simply because we have more protons in there with a roughly equivalent size atom, that means we can have more attraction to the nucleus. And so if you can imagine, if electrons are attracted to the nucleus, do you think that's going to make the atom bigger or smaller? If kind of the outside of the atom is kind of defined as where the valence electrons are. So putting that another way, if the valence electron, okay, good, Kevin got it, but if the valence electrons are feeling the nucleus more, valence electrons being negative, nucleus being positive, they're just gonna be pulled in more. Yeah, exactly. So that tells us that means that we have a smaller atom because the electrons are being pulled in. That's not quite right, is it? Being pulled in. Yeah, right. So, I have a table of these. We're going to do a few problems. Very easy math, but we'll do a few problems. So electrons are being pulled in. All right, so that tells us that going across here, let's see, silicon, phosphorus, sulfur, chlorine, and what is that, argon? Yeah, right, the best kind of math for sure. That's not silver, that's not argon. Shame on me. So that's going to tell us that sodium of this list of elements is the biggest, and argon is the smallest. And let's see if that's the case. I have them here. So the radius for sodium is 154. These are going to be in picometers. I'm just going to blindly copy. These are all in picometers, but there we go. We can see very clearly the trend here, right? So these are all calculated radii. So scientists have done all sorts of crazy things to figure this out, but lo and behold, there are the numbers for you. So I'm not lying. More effective nuclear charge is telling us we have a smaller atom, right? Because we're pulling in the valence electrons. Just because there's a more positive nucleus means more pulling in. So atoms get smaller as you go from left to right across the periodic table. All right, interestingly, we have, let's look at what happens when we go down the periodic table. Okay, yes, this is no math. Okay, well, fine. Yes, no math at all is the best kind of math. So sodium is 154. We already did that. Lithium is 134. Potassium is 196. And rubidium is 211 picometers. What do we think is happening here? Why do we think rubidium is bigger even though it has a bigger effective nuclear charge. Yeah, Kevin's got it right. Look to the simple answer. So right, the more shells we have, of course, the bigger our atom is going to be. Right? So we're going to see that there's kind of two trends that we're looking at here. And so we see going down the periodic table, even though we have technically higher effective nuclear charge, simply because there's more shells, it's got to be bigger, right? No matter how much we kind of contract that 3, n equals 3 shell, putting on another shell makes it just bigger. No way to get around that. So that's always going to be the case. So let's see what this means. Periodic table, here we go. We're going to see as we go up and to the right, we get our radius decreases. We are getting smaller as we go to the right. And we saw we also are getting smaller towards the top. And so we're going to be able to see that stuff over here is going to be real small. Stuff over here is going to be real big. So let's just get rid of those circles. So what's the biggest element, do we think? What is the biggest element going to be? Let's see if I even have a number for it. Yeah, it's francium, right, absolutely. But let's see if we have an actual number. No data. Okay, well, what about for cesium? That'd be pretty close. Where are you, cesium? 225. Yeah, that looks like the biggest number up here. So francium kind of is super radioactive, doesn't quite exist as nicely as we would like, but technically, yeah, the biggest atom should be francium. It just doesn't exist long enough for us to measure it, as it were. And so what's the smallest atom going to be? Yep, helium. For sure. Awesome. Very, very exciting. So here comes our math then. So this trend is pretty easy. Nothing too crazy about it. But let's go ahead and do more math. We love it. Math is our friend. We can use one thing that's of interest in chemistry is understanding how far two nuclei are from each other. Of course, that's probably not at all interesting to you, but these things are important, especially for pharmacology. If you want to, design a drug that's going to fit in an enzyme or something, bond length. It's important to understand how things are. There, I'll make that a little bit bigger. If you understand how the measurements are working, it'll give you better idea of kind of what drug you want to design, what sort of functional groups you want to put on there, and how it's going to fit into the pocket of the enzyme that you're looking at. For example, that's how most drug design works. So this bond length and atomic radius stuff is very important for that. Alrighty. So let's take an example. So carbon's atomic radius is 77. Sulfur's atomic radius is 102. If we imagine these guys are spheres, is this radius or diameter? These are radius. Okay, cool. If we think about it, if we now stick the carbon on the sulfur, here, let's pretend they're spheres. Carbon can be black. Okay, here it is. And sulfur can be yellow. Sulfur is a little bit bigger, right? If we stick those guys together, I feel like I'm drawing the Olympics. There we go. It looks like there's two faces, like not so happy but kissing. Anyways, so this radius here is 102. This radius here is 77. So we can imagine the bond length is just the radii added together. Which equals, what is it going to be? 179 picometers. How exciting. We can do this math. In reality, it's a little bit bigger than this. I think it's like 182 picometers. Don't worry about it. These are estimations. Is this math doable? It's too tough, I understand. Alrighty. So let's go ahead and what do I want to do with this? There's a couple things I can think of, but I don't have the numbers prepared, but that's okay. Let's say I'm going to quickly do the math in my head, and we're going to calculate it ourselves. Okay, so using the same information from before, we saw that carbon's radius was 77 picometers. What is oxygen's atomic radius? Maybe we should just go back to thermochemistry. This math is a bit too hard. Yeah, thermochemistry should be a better place to be. Yes, very nice, very nice. So, oxygen's is going to be right, the bonded one minus the carbon, which is 73 picometers. Hooray! Not funny. The nightmares are still there, huh? Well, that's too bad. Yeah, I don't care about the emails. Okay. Just so you know, you may see other units, like an angstrom. It's an A with a little circle on top. That is just the same thing as 10 to the minus 10 meters, or that's 100 picometers. So these units, you either will see atomic radii in picometers or angstroms. So either way, those would be the units you would use for this sort of thing. I want to say there's one more type of problem. Let's check. Let's check potential homework. Let's see. There may be a homework problem we can do that would maybe make us happy. No, I don't see any like numbers in here. Forget it. We tried. Okay, so there we go. I mean, I could maybe. I don't know how I could make this more difficult for you guys. This is tough. Well, you'll just have to deal with it. Okay. Yes, it's very tough. Okay. Let's look at ions. I wonder if if I have a table of that. Ionic radius. Oh, thank God, there is one. Okay. Hooray! Okay. So, let's look at two particular elements and let's see what is happening here. So sodium's atomic radius was, I just had it. What was it, 154? Yeah, I think it was 154. Sodium ion's atomic radius is 116. Oh dear, I have a network error. Let's hope this gets fixed. Yeah, it's fixed. Okay, cool. Fluorine's atomic radius is going to be, or fluoride is 119. I have to look up fluorine. It sucks that these numbers are not so easy to memorize. But anyways, let's have a look. What do we see here is a trend. Okay, bye, Kevin. Yeah, I had the same thing, so that may have been on me as well. But let's take a look. What do we see has happened here? Is that so? Take another look, Tyler. I'll give you another example, perhaps. Let's see, oxygen. Oxygen, okay. And why not, how about we do magnesium also? That's better, that's what I want to see. Okay, magnesium is 130. And magnesium 2 plus, is, where are you? Magnesium 86. You are absolutely right. Absolutely right. So cations are smaller than their atoms would be. And anions are larger. Why? So again, these numbers, I mean, there's no need to like memorize these numbers or anything like that. We're just looking at trends here. So why do we think that cations are going to be smaller than the regular atoms they represent? And interestingly enough, What do we notice about these two? Electron configuration wise. Actually, all of these have something in common. But let's getting ahead of ourselves. Let's just think about why the cations are getting smaller. Why do we think this is? Why would a cation be smaller? Okay. Yeah, there's definitely loss of electrons going on. Kevin, I think, has the the one that I was going for. Yeah, we've basically gotten rid of our shell, right? Like sodium used to have an n equals 3 shell. We've completely gotten rid of it. We have lost that valence electron. So our new valence electrons are actually in shell number 2. So that's great. Hooray. That's happy things for us to see. Alright, same with magnesium. We would have gotten rid of that outermost shell. And now we've kind of just completely shed it. And so that's why we're smaller. Okay, and then so the anions, why do we think those are going to be bigger? Where is neon? Okay. Neon. Not quite gaining shells. I mean, that could be a possibility, but that's not necessarily what's happening in this case. This one is not quite the opposite. So let's take a minute. Let's look at the electron configuration here. So we're not quite losing a shell, but yes, we're gaining electrons, right? And what do electrons? So electrons don't want to be together, right? We are effectively, that extra electron is going to mess with our effective nuclear charge. Right? So electrons don't want to be near each other, right? They want to be as far from each other as possible. They're negatively charged, right? So putting in more electrons are going to cause the atoms to spread out more. Or sorry, the electrons to spread out more. So adding electrons is actually going to reduce our effective nuclear charge. So you can imagine the electrons that we're putting in that outer shell are now going to push each other away further. And so we're going to kind of expand our atom a little bit. All right, so does that kind of make sense? So where we went from to, what did we go to? Helium. Why am I even writing helium? We have completely lost our third shell for sodium. But in the opposite case, the adding of electrons, we're just having them repel each other. They're just pushing each other away from each other. And so it's expanding. Whereas the cation, we completely lost our third shell. Okay, so that's what we're looking at here. So notice, if I draw these, let me see here. So magnesium is smaller than sodium, which was smaller than fluorine, which is smaller than oxygen. Those are just from the numbers we have here. If we're to use our predictive power, where do you think we would put nitride in this order of things? Where do we think that's going to be? So Kevin, smaller than oxygen or bigger than oxygen? Because I think we should put it here. I think maybe you had flipped it in your mind. But yeah, I think we're going to put it there. And so I just looked it up. Nitrogen is going to be 132 picometers. Let's just see. Oxygen was 126. So yeah, we've made a bigger thing. This is what's called an isoelectronic series. They have same number of electrons. All of these have the neon electron configuration, and so they all have 10 electrons. Let's take a look at their effective nuclear charge. So, if we think originally magnesium had an effective nuclear charge of 2, 2 positive, and if we get rid of 2 electrons, that's going to make things even more positive, right? So we started at 2. We got rid of 2 electrons. So this is roughly 4. Roughly 4. And sodium will be... Actually, it's going to be bigger, isn't it? Bigger than 4. Because we now have our core electrons are now valence electrons. Whatever. The idea here is that this is going to be the biggest effective nuclear charge. And this will now be the smallest. So if we think about nitrogen's nucleus pulling in valence electrons, if we keep throwing more valence electrons on there, they're going to be kind of competing for that nucleus, right? And so if they're competing for it, like the nucleus is not going to be able to pull them in. If those were all their ions, yeah, that would be an isoelectronic series as well. And we're going to see here that the size trend will be kind of the same thing here. So that the more negative we go, the bigger our atom gets. And the more positive we go, the smaller our atom gets. So let's go ahead and do that. So with the ones Tyler has put in here, he says... arrange these in size order. And let's go ahead and say that these are ions. How might we arrange these from, let's say we're going to arrange it from biggest to smallest. Forget doing any math. Let's just do it intuition-wise, as it were. Looks good, Kevin. Oh, Tyler, I switched it on you. I said biggest to smallest, so you have in fact done smallest to biggest. Haha, gotcha. Yeah, so indeed, the biggest one is going to be the phosphide ion. Then sulfide, then chloride, calcium, potassium. Oh, I'm sorry. I switched those two, didn't I? I just reversed the order up top. Same on me. So, there we go. So that's not too bad. Does that make sense to everybody? Can we all do this? Provided we read the question properly. Nah, just joking with you. But let's just remember. Now we're sad. Oof. Okay, so, cool. Is this part okay? Alright, I'm thinking it's okay. These parts should not be too bad. We have more trends to talk about. Metallic character. How exciting. Where are our metals on the periodic table? And where are our non-metals? Whatever, there's our fancy line. So ignoring this crap here, where are our non-metals? Or metals? Choose. Tell me something. Mm-hmm. So, trend is going to be super easy for us. Just from knowing where our metals and non-metals are on the periodic table, we can already kind of see that. Here, I can redraw our little step ladder thing. Whatever. We can see that as we go up, for example, we have lead down here, carbon up there. As we go, we know lead is pretty metallic, right? It is shiny, it is gray, it is hard, it is conductive, all that fun stuff. Whereas we look at carbon, it is brittle, it is black, at least in terms of graphite. It is does not conduct electricity. I guess graphite does, but that's a special case. Does not conduct heat. Carbon's definitely non-metallic. Lead is definitely metallic, right? So we're going to see that if we go up on the periodic table, we're going to become less metallic, more non-metal. And as we go to the right, of course, that's where we also get less metallic. So same thing here. Size and metallic character are the same trend. So like helium would be our least metallic of all the elements, and francium again would be our most non-metallic, or most metallic rather. So that's kind of boring. So there we go. Very exciting. We don't really care about that trend as much. But we're going to see that things that are on the left and the bottom will tend to lose electrons. They're going to tend to be more metallic. Things on the right and on the top will tend to gain electrons, and they do not have the properties of metals. So they're going to be, different states of matter, different colors, non-conductive, etc. That's a boring trend. Who cares? All right. Another trend. First ionization energy. Ooh, exciting. Let's define this. It's the energy that's required to remove an electron from an atom. It always requires energy. Anytime we are losing an electron, we have to put in energy to make that happen. Is that exothermic or endothermic? I guess it's not necessarily thermic. There's a better word for it, but we haven't learned it yet. Yeah, essentially, wait a second. No, endo. Yeah. We have to put in energy. So this is telling us that, for example, to blast off our electron, we need to put in energy. So if we think about how we put in energy to make electrons jump up to different orbitals, or we put energy in to do that photoelectric effect, remember, we put in energy, we shine our X-rays on our thing or our UV rays, we blast off an electron. That's the kind of the same idea here, is that we have to put in energy to do it. It turns out, if we can think about how atomic size is related here, we saw that sodium and then magnesium and aluminum, silicon, phosphorus, sulfur, chlorine. We saw two, what were the atomic radii for this? I can maybe copy them because where did we write these? Aha! Let's just copy this stuff. Well, no, we'll copy that too. Cool. Okay, goodbye. Other words. Oh, okay, that's better. So, if we think about this, if we are looking at these valence electrons, we can just look at the radius to understand that a big radius means the electrons are really far, right? It's a big thing now. Whereas argon, they're pulled in, right? We contract our radius. We've pulled in our valence electrons close to the nucleus. And so looking at this, which one do we think it's going to be easier to take an electron from? Yeah, it's going to be sodium, right? The sodium is really big, so it's not as attracted to the nucleus, so it would be easier for something else to just knock it out of place or to take it from it. And so we're going to see that this, just erasing the biggest and smallest here, looking at the ionization energy, it takes a little amount of energy to take it from sodium, but a large amount of energy to take it from argon. Let's pull up some numbers. Where is a... yeah. Oh, thank goodness we have them all here. Okay. I'm going to erase our atomic radii. Goodbye. And I'm going to put in the ionization energies so we can just see the trend. Let's see. Let's put them in light blue again. Sodium, 496. Magnesium. Ooh, I don't want to talk about this. But we'll do it anyway. $1,000, 1256. These are in kilojoules per mole, by the way. Last one is 1520. Okay. Indeed, the bigger the atom, the smaller the ionization energy. Interestingly, we have two blips here. We have two kind of exceptions going along here. Let us think about it. This is kind of an interesting... Shane, you got it right on the head. Very, very nice. Very nice. Wow, I'm glad you remember that from yesterday. Yeah, you guys have got it right on the head. So, if we think about our... we have... so, sodium. Boom. To take its valence electron away, there it goes. It's gone. If we look at magnesium, to take its valence electron away, boom, we're left with a half-full orbital. Not necessarily bad. For aluminum, we're going to completely vacate our p shell by getting rid of it. So we're left with still a full orbital. Remember, full orbitals are a very good thing to have. So that's a good thing. But I think the most interesting one is going from phosphorus to sulfur. So phosphorus is this. And I'm just going to put sulfur as extra electron in blue. So we can see that it's actually going to be less energy to leave this half full than it is to get rid of that guy also. So Shane, you got it right on the head. I'm not going to necessarily ask you to explain this, but this is why we see these little blips there. It's just because of, as Shane has said, because they are at a state they like to be in. And that is absolutely right. So remember, full valence shell, half full, and empty, those are good things. So, yeah, that's kind of the reason for that. But suffice it to say the trend is pretty obvious, right? We can see that the bigger the atom is, the easier it is for us to grab the electron off. So let's not worry about the blips. Let's just kind of understand that these they're related to the size. There we go. That's what I'm trying to say. I have some more things for us to show. So first ionization energy is to remove one electron. I'm just going to throw out some more numbers at you so we can see some behavior. We have what's called second ionization energy as well. That's the energy to remove a second electron. And the third electron, fourth electron, and fifth electron. I'm going to just copy numbers here. But let's take a look at another trend that we have. So I hate just copying numbers down, but you guys don't need to remember the numbers by any means. You don't even need to copy them. They'll be here for you, but I want to show you something. 2281, 11, 6000. Silicon 786. 1577. 3228. 4354 16100. Okay. Enough of this nonsense. With our understanding of what ions these things like to form, do we see any trends in this data? Remembering that these are basically how much energy to remove that electron. So energy to remove the first electron, the second electron, the third electron, fourth electron, fifth electron, etc. We can go all the way to 7 electrons, but who cares? We don't need that much data. What do we notice? What seems suspicious about this? It looks like a staircase. Yeah. Oh, well, I mean, that's just because sodium would not lose. I mean, it'd be incredibly difficult to get rid of the other one for sodium. But yes, it's that staircase idea. Tell me more about the staircase. That's right, Shane. Absolutely. So we know, for example, sodium likes to lose 1 electron. No problem. And Kevin, you've got it exactly right. Also, you both have it perfect. You've just kind of changed the phrasing a bit. It's going to be a lot harder to remove the second electron from sodium. Sodium likes to be +1. It's not going to want to remove another one. Then it would have a full valence shell. Kevin's just more scientific. That's true. That's true. But both of these are happy. But yeah, we're looking we see these dramatic increases, as it were, once they have gotten to where they want to be. So we see that, it's great. Magnesium can lose its 2 electrons, no problem. But losing the third one is going to cost way more energy. For aluminum, losing a 4th one, way more energy. Silicon, same thing. So that's the trend here. So we see a large increase in ionization energy after the preferred charge. Ooh, that's not how you spell preferred. And so you're going to see a homework problem next week where I'm going to give you a bunch of data like this, and I'm going to ask you, here's this mystery element. Tell me what charge it prefers. Yes, Shane. I do have the numbers for that, but they get more complicated. So we're going to see that. So sulfur will have a gap between its 6th and 7th one. And phosphorus will have a gap between 5th and 6th. So while you are absolutely right, phosphorus does not want to be +5. It would rather be +5 than +6. For sulfur, it would rather be +6 than +7. That's the idea. So yeah, I mean, of course, at that point, we're already in absurd energy amounts anyway that are in crazily high kilojoules per mole. And so we're going to see that. So tomorrow we're gonna start, not tomorrow, Monday we're gonna start with electron affinity, which is the opposite of this. And so we're gonna see there that it's gonna be the same case but just in reverse. So last kind of things here. This is one thing about ionization energy. Another thing is that ionization energy increases as size decreases. Okay, so we have 2 things to worry about with ionization energy, and that's it. So again, we're not really doing math here. We are just looking at trends. Okay? Alrighty, so tomorrow we'll have exam review if you want. Post questions in Discord, take your screenshots, post them up. Trendsetters indeed. And so if you want to show up to that, I'll be here 10:15 tomorrow. Other than that, I'll see you on Monday, I guess. So enjoy, have fun, and I will try and grade your stuff today. So I will actually go into my office and do that, so I don't even have the option to do fun things instead. So, yeah. Okay, cool. See you guys later.